Hey there, math physics people. I sent out a video that you hopefully watched already. It's the same thing we covered in class. I'm doing example 3, the roller coaster problem on page 128, and the free fall problem, example number 1 on page 127. Number 1 and number 3 on those pages 127 and 128 are the best to illustrate the law of conservation of energy. Now, energy transfers back and forth between kinetic energy and potential energy. Remembering that the law of conservation of energy says energy cannot be created or destroyed. It may be transferred from one form to another, but the total energy of a system remains constant. Number 2 is one that if we had a non-COVID situation in class, we would spend more time on talking about some pendulum ones. This is maybe not as necessary to know to understand the subject material, but it's just a good enhancement to help understand kinetic energy, potential energy, and the whole relationship between those two with mechanical energy. So let's take a look at this pendulum example. Last week in class, I had that big pendulum in my classroom. It was almost 18 feet tall, and I pulled that pendulum back to my face and I let it go, and you saw it go out and come back and almost hit me in the face. Almost came right up to the exact same spot because the total energy in the system stays constant. And we know that eventually the energy will transfer into the air molecules and eventually that pendulum will slow down. But in the first couple of swings, that pendulum would go out like 15, 20 feet and swing back and almost get to its same height. So here we're actually looking at a pendulum that's 2 meters long. So that's about 6 feet or so. And we're going to pull it back 20 degrees and let it go. And we're asking to find the maximum height and the maximum velocity. And at first look, it's like, well, how do I possibly find those things out? And here's a little twist and a little difficult thing about a pendulum. So the first thing I have to do is I'm going to assume the pendulum at the bottom has 0 height. And it's okay to assume that unless we were told otherwise. So what I'm going to do is draw a little line representing the floor. And we're going to pull that pendulum back a certain amount, in this case 20 degrees. So that pendulum's pulled back. And I'll exaggerate, that's obviously more than 20 degrees, but I'll exaggerate it for the effect of doing the problem. And there's my pendulum. Pulled back 20 degrees. So on my picture, I know what the height would be. I can sketch that actually. My height is going to be that much above the ground. That's the value I have to find for part A. And once I find that value, the other things being asked for are going to be easy to find out. So how do I find that height? Well, believe it or not, finding that height and solving for part A is really not a physics problem. It's a math problem. Just simply math. I'm going to draw a right triangle. And I think you'll probably start to be able to see where I'm going with this. I want you to focus on that green triangle. Now, what do I know about that green triangle? Well, I know that the length of the pendulum is 2 meters, regardless of where it is. I'm just pulling it back here, and I let it go and it sways back and forth, but the string is 2 meters long here, which means it's 2 meters long there. So I'm actually going to look at the green triangle and do a little trig problem, where I can say the cosine of 20 degrees equals my adjacent side, I'm going to call that x, over the hypotenuse. Well, the hypotenuse of the green triangle is 2 meters. When I do that, take the cosine of 20 times 2 meters, I get 1.88 meters for x. So that means this value right there is 1.88 meters. And I'm looking for this value right there, which is my height. Well, 1.88 meters plus h must equal 2 meters. Therefore, H is 0.12 meters. So finding the height, answering part A, is nothing but a trigonometry problem. And hopefully you caught that. If not, you can obviously rewind the video and watch it again. So there's my part A. H equals 0.12 meters. Part B says, what's its maximum velocity? And here's kind of the cool thing. Might be a little confusing, but the cool thing about pendulums. The mass doesn't make a difference. So watch this. At the top, whoa, that's weird. At the top, all the energy, the total energy, is in potential. Because at the top, the pendulum comes to a stop, so the kinetic energy is zero. Remember, kinetic energy depends on an object's velocity, where the potential energy depends on an object's height. So at the top, I know the pendulum comes to a stop. If it didn't, it could never come back down. So V is zero at the top. So KE is zero at the top. So all the energy, the total energy, exists as potential, MGH. At the bottom, it's just the opposite. At the bottom, the total energy, which cannot change, law of conservation of energy, exists as kinetic energy. Because at the bottom, it has no height. Well, if it has no height, it has no potential energy, so all the energy must exist as kinetic. So what I can actually say for all pendulums is this. I can say that the potential energy at the top equals the kinetic energy at the bottom. Because the total energy at the top has to equal the total energy at the bottom, has to equal the total energy halfway through, and the total energy everywhere. So total energy equals total energy. Well, all that total energy at the top is in potential, all that total energy at the bottom is in kinetic, so the potential at the top equals kinetic at the bottom for any pendulum. Which means MGH at the top equals 1/2 mv squared at the bottom. And those of you who are mathematicians can see what happens is the mass actually cancels out. Now you can put in the mass of 5 kilograms, which is said in part C of the problem, but you actually don't need to. The mass is irrelevant. Anytime something cancels out, it's irrelevant. So what that tells me is G times H equals 1/2 V squared. So 2GH equals V squared. You can divide by 1/2. I like multiplying by 2 better. So V equals the square root of 2 times 9.8 meters per second squared times the height at the top, 0.12 meters. I'm going to calculate that out. I get a V of 1.53 meters per second. Just by setting the potential at the top equal to the kinetic at the bottom. Part C says if the mass is 5 kilograms, find the total energy of the system. Well, I can find the total energy of either doing the potential at the top, because that's the total energy, or I can find the kinetic at the bottom. Either one, I'll get the same answer, give or take a little bit for rounding. So if I wanted to find it at the top, I would say my potential energy at the top is MGH. So it's 5 kilograms times 9.8 meters per second squared times 0.12 meters. And that will find us an energy of 5.88 joules. If I wanted to, I could find the kinetic at the bottom. So, or I I can do kinetic energy at the bottom, 1/2 mv squared, and you'll get about the same, 5.88 joules. Might be like 5.85 or 5.83 because we rounded a little bit, but you get the same number. So to find the total energy, I can find either the potential at the top or the kinetic at the bottom. Both are going to be the same amount because energy is conserved. So a little bit different of a problem. Don't get too worried about this if that didn't make total sense. It was just used to add extra enhancement to our understanding of potential, kinetic, total, and the law of conservation of energy. So, all right, have a good day. We'll see you guys soon.